today's lecture is a continuation of chapter 4, total and effective stresses. In the total and effective stresses, we first started by studying the stresses within the soil due to the own weight of the soil. Then we took another section for the stresses due to external load, and we said that external load may have three types. It may be concentrated load, it may be line load, it may be distributed load. We studied the concentrated load, and we had a chart for the concentrated load, something like this. And then we studied the line load, and we had a chart for the line load to help us in this. And then we came to the distributed load, and we said that this distributed load may be square or rectangle. It's an area. It may be square or rectangle. In this case, we can use this chart. And we said some cases about this to use this chart. Then we said that there is an approximate method. This approximate method, it does not calculate the stress at a point. It calculates the stress below the footing at an area. So from the name, giving it as an area, it's an approximation, because in any area the stress will differ from one point to the other. So what is the value given here? It's just an approximate value. So but we have to say it because we use it a lot in engineering, because in engineering we do not care a lot about a point in the soil. We care about areas, because if we have settlement for a building, it will not being affected by one point. It will be affected by a whole area. So it is okay for our use in our geotechnical design. And then we said that there is a uniform or something general that can be used for anything, which is Newmark chart. And we said that it is a very brilliant method to calculate, but to approximate calculation based on manual calculations. This Newmark chart, it has just a line at the bottom. This line is the scale. It's the distance AB. I use a tracing paper outside. I get the tracing paper. I draw the footing, my footing on this tracing paper. Tracing paper ورق شفاف. So I put it on a tracing paper, and you see this one here. Suppose I have this is my footing. It's something irregular. It's not square, rectangle. It is an L shaped, and I need to calculate the stresses below, at a distance below this point. So what is the below? How many meters below? If I tell you 5 meters below, then I should draw this footing with a scale. What is this scale? This length represents the 5 meters, which is the depth. So if I manage to draw this, I will take it, put the tracing paper with this point N on this center. I just count the number of four-sided figures here. As you see, below is the number will be very high, but as we go outside, all of this is 1 square, but this small one is 1 square. So when you are near the point of application, the number will be higher. So I just put suppose I have a square footing, I will put it here like this, and I need to study the stresses below it. So I put the center here, and then just count. After counting, put this N here, multiply it by the stress, and I will get the additional stress due to this footing. Now I go to another thing. This other thing is called, I need to study the types of stresses in the ground itself, not the external. Now I'm back again to the internal stresses, but I need to differentiate between different types of stresses. We said that if I have at this point, I have here point A. I want to study what are the stresses in point A. The stresses in point A, whether it is due to external, internal, I don't care. Here I'm not speaking about the stresses caused by internal or caused by external. No, I'm just speaking what are the types of internal stresses at this point. So at this point, I have always something called sigma 1, which is the vertical stress. Can anybody tell me what is the vertical stress at point A? For the case you have now, this is the ground surface, this is the water table, and I have a point here. Can anybody tell me what is the internal stress, vertical stress sigma 1 at point A? Q? No, it's at any. So at any point, what concerns me are two things. Actually, they are one thing. What is this one thing? The length of this column of ground. If I have here at this point, above me there is ground. What is the depth of this ground and what is the unit weight of this ground? So actually, sigma 1 is in any case gamma by h, or sigma gamma by h. If you have different layers, then each layer you will calculate the h, multiply by its gamma, and the other one h by its gamma, and so on. So sigma 1 is sigma, the summation of all gamma h's above me. Then I have sigma 2 and sigma 3. What are sigma 2 and sigma 3? Sigma 2 and sigma 3 are the horizontal stresses. We said last time that vertical stresses induces horizontal stresses in soil, and we said what is the example of this? It induces horizontal stresses in many things. Any body, any fixed body, if you subject it to vertical force, you will find that the shape will differ. If I have, say, clay, a piece of clay, and I salsal, like the one that we play with when we were small. If you subject it to vertical force, you will find it bulging from the sides. Bulging from the, how did it happen that the cube started to move from the sides? It means that there is force from the sides, and it happens all over the side. It will not bulge in one direction. It will bulge all over the sides of this cube. So if I squeeze this point A with sigma 1, then I will have another stresses sigma 2 and sigma 3, and in many cases sigma 2 and sigma 3 are the same. They are equally the same, unless the soil is what we call anisotropic or anisotropic soil, which means that it does not have the same stresses in each direction. It differs as a soil. So these are sigma 1, sigma 2, and sigma 3. Now these sigma 1, sigma 2, and sigma 3 are the stresses, but we said that in case we have water in the soil, water will carry. It's not only sigma 1, sigma 2, and sigma 3. There may be sigma due to water. How will this happen? Imagine that you are standing on clay, and this clay is full of water. If you stand on clay, you want to squeeze this clay, but the clay contains water. So what will happen? Water will try to leave the area below you, but to leave the area below you and go outside, it needs to do some kind of seepage in the soil. But clay is very, very poor in seepage. So what happens is that the water will be trapped for a while. So in this time, water will be carrying part of your load. So you are standing on the clay. It's not clay only who is carrying you, clay plus the water. Then if you wait for a while, some of the water will percolate away. It's going to seep away. So what will happen? Part of the load carried by the water will be transferred to the soil. And so on till all of the water is expelled and your load is carried by the soil itself only. So in this case, I have three things to check. I have sigma 1, sigma 2, and sigma 3. These are the total stresses. It is your weight. If I say sigma 1, then it is your weight. It is the effect of your weight on the soil. But if water is carrying part of it, then take the stress of water to be equal to U. U, call it U. Here, the stress of water is called U. But the stress of water is constant in any direction. Water is isotropic. The stress at any point in water is the same in all directions. You don't have any difference between vertical stress, horizontal stress, any inclined. All of them are the same, equal to U. So I have sigma 1, sigma from here sigma 1, here sigma 3, and on the perpendicular direction sigma 2, and I have U all over the body. Then I should calculate something called the effective stress. So I have a total stress, which is sigma 1, sigma 2, and sigma 3. This is total. It includes the effect of the additional effect of your weight on the soil. But part of the effect of your additional weight on the soil is carried by water, so it is U. So if I want to calculate the effective stress, which is, instead of sigma 1, it is sigma dash 1. Instead of sigma 2, it is sigma dash 2, and so on. What it is equal to? It is equal to sigma 1 minus whatever the water carries, minus U. So now this is the important relation that we want to reach, that we have sigma 1, sigma 2, and sigma 3. These are the total stresses due to additional load on the soil. Part of this load is carried by water and it is equal to U. In the direction of sigma 1, it will be U. In the direction of sigma 2, it will be U. There is no U1, U2, U3. It is U in all directions. So if I want to calculate something called sigma dash 1 or sigma dash 2 and so on, which is the effective stress excluding the effect of water, then it will be sigma 1 minus U, or sigma 2 minus U, and so on for sigma 3. So this is the another thing that we want to stress. By the way, we are just taking basis for what we are going to study in coming lectures. So this one you will go to study thoroughly in the next lecture when we study shear strength. But if I start with the shear strength and start to give you the principles of the stresses, then you will get confused. So now we are trying just to understand this ABC, and then next lecture when we go to shear strength, then we can build on what we have understood. Another thing that I want to introduce is something called Mohr circle. Mohr circle is also something very something like Newmark chart. It's a graphical presentation to solve a problem. Of course, it is made by a scientist called Mohr, and his presentation is very good, and it helps us a lot in calculating the shear stresses in soil. We are not going to study how he reached this shape. Similar to, we did not study how Newmark reached his shapes. These circles in each other, this circle in each other's subscribed inside each other. We did not know how he got it, but he got it based on studies and equations. Similar to what here more done, he just drew these two axes. This axis represent the shear stress, and this axis represent the normal stress. So what is the difference between the normal stress and the shear stress? If I have normal load on the soil, then it will induce normal stress. Any load divided by area give us stress. But shear means something. If I have a foundation on the ground and this foundation is pushing the ground, then it wants to shear the ground, it wants to go down. So the ground to move, the particles of the soil has to be sheared. So it's another type of stress. The first stress is the load divided by the area. This is a normal stress. But this normal stress will cause shear stress. Why? Because this normal stress wants to penetrate the soil and go deeper. What prevents it from this neighboring soil? Neighboring, this footing is on top of the soil. It wants to shear the soil and go down. What prevents it from shearing the soil and going down? Particles around it. Suppose that I'm putting this mobile, which represent the footing, in water. What will happen? It will sink. Why? Because there is no shear. When I put the mobile on water, I can calculate the normal stress, because I will just divide the load of the mobile by the area of the mobile. This is the normal stress. This normal stress is very high for the water. And the water does not have any shearing stress. So what will happen? It will shear the water and it will sink down. So this is failure by shear. Suppose I replace the water with something a little bit stronger, maybe a very loose type of soil. When I put the mobile on the top of the soil, it will not sink to the bottom, but it will penetrate maybe 15 centimeters. So it sheared also the soil. There is some kind of shear strength, but the shear strength of this soil is still less than what than the stress that I'm inducing to the soil. If I put the mobile in the third case on top of very strong soil, what will happen? Nothing will happen. Maybe the mobile would break, because if I throw it on top of it, it will break. But if I throw it in water, it will break. It will get harmed also because of water, but it will not break. It will be harmed in one piece. But if I put it on top of, throw it on top of the ground, it will smash into pieces. So why? Because the soil is strong and it has shearing stress. So I have something called shear stress and I have something called normal stress. In this chart, we said here that we have sigma 1, sigma 2 and sigma 3. And we said that in many cases sigma 2 and sigma 3 are the same. So consider that we are speaking about sigma 1 and sigma 3 only. Sigma 2 is the same as sigma 3. So Moore presented this drawing. This drawing, in the normal stress axis, I just put the value of sigma 1 and the value of sigma 3. This is the high value of stress here, and sigma 3 is the low value of stress on this particle. and I draw a circle. When I draw a circle, if I go horizontally tangent to this circle, then this will be the shearing stress that would cause failure. It means that if I have this block and I'm subjecting it to sigma 1 and sigma 3 in all directions, it will stay in place, it will not fail unless this point A cannot take a shearing strength equal to this value. From this point, go horizontally, cut this point in here, then this is the value of shear strength of soil that should be there so that the soil can take sigma 1 and sigma 3. If I have in the soil sigma 1 and sigma 3 less than that, so what will happen is that my sample will be sheared. So this is a presentation of sigma 1 and sigma 3. We said that we have water. This is based on having sigma 2 equal to sigma 3. If I have water, then to calculate the effective stress, we subtract from sigma 1 water and we subtract from sigma 3 water. So I have another circle, and this circle I can draw it. It's called the effective stress circle, and this is the total stress circle. This just an introduction. It will help me next lecture when we study shearing strengths, so it is important. The last part of the lecture is discussing the volume change. What will happen to the volume of the soil in case I subjected to stresses? As we know that soil particles are solid. If I stand on top of sand, do I expect that the sand particles will get affected? No, they will stay the same. Sand particles will be the same. Whether I stand on top of it or I take it in my hand, it will still be the same size of sand particle. But what happens is the voids between the sand particles get compacted. So when I subject the soil to stress, what happens is that the voids are affected, not the soil particles. Suppose that these voids are full of water. What will happen? Water is going to be expelled outside. But to be expelled, it has to follow a seepage path. To follow this seepage path, it depends on the permeability of the soil. If I have soil that has high permeability like the sand, then water will go quickly. If I have clay, water will take a very long time to leave the particles. This is here what we were saying. Here, in case I have this is compacted and this is compacted. Look at the particles. The particles are more or less the same in both figures. But in this one, I have air. I don't have water. Maybe the color here was not very clear, but here I have air, not water. If I have water, then the voids here will be water, and I will be trying to expel water outside. But if I don't have water, it is just air, then any additional load on the particles, they will get nearer to each other without any problem. But if I have water, then they will have to expel water first before getting near to each other. That's why if I'm standing on a clay with water, I may, not me, suppose I have a building standing on sand and building standing on clay. The building standing on sand, once the load is applied, the sand will settle and that's it. But the building on top of the clay, like in places in some places in Alexandria, you find that the building maybe after a year and it is still sinking in the ground. How is this happening? Because it is still expelling water, and once it expels the water, the voice diminishes and settlement happens. So this is just an introduction to water in the soil, but these charts are very important. In soil we have two conditions. Condition called drained condition and another condition called undrained. Drained means what? Water leaving. This is drained. When I tell you drain something, it means that take water out of this place. So what is drained and undrained condition? This is related to laboratory testing. The example that we just said, I have a building on sand and I have a building on clay. If I have a building on sand, once the load is applied, if there is water, it will be expelled immediately and the building will settle. If I have building on clay, it will take longer time. If I want to make an experiment at the lab to simulate both the sand and the clay. So for the sand, I have to simulate a case of drained condition. Why? Because water is either not there, or if it was there, it was expelled very quickly. So it had no effect in my test. So I should do a test which is drained test. But if I am simulating the clay, then I should, especially at the beginning, when I want to simulate the onset of the test, I should have it undrained. Why? Because water will be trapped. Water will not be able to leave. But maybe after an hour it would leave. Maybe after a month it would leave. I don't know. But it will leave later. But at the start of the test, I should study a condition called undrained test. Undrained means water is trapped and cannot leave, and it is sharing in carrying the load. So this is the difference between drained and undrained. Let's study first what is a drained test. Drained, which is similar to sand, it means that when I apply the load, water will leave very, very quickly and it will not have any effect. So look at this chart. Between the stress, this is a relation between the total stress and the time. All of the next graphs are studying the effect of anything with time. So I start my test here, and as the time passes by, the stress increases because I'm putting load all the time. I put load, the stress increases. So the first graph just show me that I started with a certain stress, and then this stress increased. Suppose I'm standing on the ground, then here will be my own weight. And then every time you give me something to carry, so my weight is going to increase. If you give me 1 kilo, then my weight will increase by 1 kilo. Then you give me 10 kilos, my weight will increase by 10 kilos. So as time passes, your weight is going to increase till you reach the maximum that you can carry, and then nothing will happen again. So this is the first graph showing the relation between the total stress, which is the total weight on the soil, compared to the time. Here, another two charts. One of them, both with time, but here it is the pore water pressure. The pore water pressure, if I start here with pore water pressure with a certain value, I will end up with the same pore water pressure because nothing happens. Water can easily leave and can easily go. If it was there before loading, then it will stay the same after loading. So water has no effect. What about the volume? Here I am increasing the load. Once I increase the load, what will happen? The soil will be compressed, so the volume will decrease. So I increase the load, the volume decreases, increase, decrease, and so on. So if you compare this one to this one, you will find that once you increase the load, you reduce the volume till you reach the maximum reduction in volume compared to the maximum increase in stress. The third or the fourth graph in the drained loading is the effective stress with time. What is the effective stress? You remember we said that we have a total stress, we have a stress of water, then the effective stress is the total stress minus the stress of water. So actually, to draw this line, what do I need? I need to subtract this line from this line. So this line is a constant. So I will just, what will happen is sigma naught, instead of being here, maybe it will be a little bit below, but the curve will stay as it is because water has no effect. So here you will find that it is exactly the same shape of this, and delta sigma here is equal to delta sigma dash here. But the difference is in the starting point. Instead of having the starting point here, it became a little bit low. How much is this lowering? This lowering is equal to this amount U dash, U naught. So we just start from here. So now I have 4 drawings giving me the different conditions in case of drained loading. Let's see the same 4 drawings in case of if I have undrained loading. Undrained loading means what? Undrained means it is something like the clay, where I will give the stress, but water is not free to leave. Or it will be free to leave, or it will start to leave after a while. So what will happen? I will draw a graph for the total stress. Let's see here. I added the load till I reach the maximum load at the end of my test. But here you will find that you will start with the same point, but you will reach your maximum very quickly because water is carrying part of your load, and then it will stay like this. So this is the total stress. Let's compare the volume. If I have here the volume here, it was, as we said, the volume here was opposite to the stress. The stress increases, the volume decreases. But here, the stress increases like this and stay constant. So with the first portion of my graph, the volume is not going to change. Why? Because the voids are full of water, and the water is not free to leave just push a bottom and water leave. No, it will take a lot of time, or take some times. This time is here. From here to there, the volume will stay constant. Then water will start to seep, and it will not seep very easily. So in this case, the volume is going to decrease, but it will take very long time to reach the required change. Last thing here, the effect of water. Now we want to study water. What will happen with water? If I start water with U naught, by the way, in all tests we start with always U naught, V naught, anything. This means the start of the test. So with the start of a test, I start with sigma dash naught. For a while, I will stay the same because nothing happened. Because you remember we said that the effective stress is what? Is the difference between the total and water. This is water and this is the total. Just subtract these two graphs from each other. Subtract this one, subtract this one, which is the total stress, minus the pressure of water. You will end up having this chart. At the beginning it is constant, then the total stress the effective stress start to increase. Can anybody tell me why the effective stress increases? Without going into this, why in this test the effective stress increases? What is the meaning of the effective stress increasing? Anyone can think? Effective stress is the stress carried by the soil. If I tell you that the effective stress, which is the stress carried by the soil, is increasing, it means that the contribution of water is diminishing. Water is consolidating, water is seeping outside of my loaded area, and when it goes out, the load carried by this amount is transferred directly to the soil. So actually, I start with here with sigma dash naught, and then I will stay there for a while till water start to seep. Once water start to seep, then I will have this increase. To end the lecture, this is just a comparative figure. These are the drained cases. This is the drained response. This is the undrained response. The drained response represents the response of sand. The undrained response represents the case of clay. Here is the total stress. Here is the volume. Here is the pore water pressure. Here is the effective stress. So start with the total stress. If I start at point, this is the start here should be similar to the start here. But here I reach the maximum at a very long time, but in the case water is not leaving, then I reach the maximum very quickly because no compression happens to the sample. Then the full volume, the full sample carries the stress very quickly. What happens with the volume? I said the volume is the opposite. Here it is the opposite of this chart. When I increase the stress, the volume decreases. Here, when I increase the stress, the volume does not change at the beginning because I told you the water is trapped. So it has to have some time to be pushed. It will not just you just put the load, it will go. No, you have to discuss something. Please leave. We have some load coming, and so something like this. So at the start, you have to wait for a while till water start to seep outside. Once it starts to seep outside, then the volume will decrease gradually. So this curve is completely different than this one. So the case of drained is completely different than the case of the undrained. Here water response was constant all over the test. Here no, it starts from zero, from the start point, and then increases very quickly because water is not permitted to leave, and once it is permitted to leave, then it starts to decrease gradually till it reaches the starting point. Effective stress, we said that the effective stress is just the subtraction of the total, which is this one minus the pore pressure, and here also it is the total minus the pore water pressure. So if you subtract this minus this, you will get this shape. If you subtract this minus this, you will get this shape. this is very difficult. To tell you the truth, it is difficult how to understand the total stress, the effective stress, sigma 1, sigma 2, sigma 3. It is very difficult to understand. But if you concentrate and try to understand what is given here, it will be easier for us to go to the next lecture. So I tried my best to put it in a way that you understand all the differences, what happens in terms of the total stress, which is your load acting on the ground, what happens in terms of volume of the soil beneath you, what happens in terms of water that is next to you, to the clay, to the particles of the soil. Will it carry load or will it not carry? It will not carry load in case of drained case. It will carry load in case of undrained, but it will carry it for a while and then will leave it because it will leave. And the effective stress, this one, actually we are keen to know what is this, because when we come to design our foundation, we use the effective stress. So maybe here it is not a big problem, but here it is a big problem because this value of T may be years. So imagine you want to design a building that is safe now on the case of total stresses, and it will be safe maybe 2 years later when all the water is expelled and the effective stress reaches a different value. So just few information, maybe when we come next chapters you will know it better. But to be it is better for you that you read this lecture again, so that when we come to the, if you are confused now, then when we come to the shear stresses, you will be more confused. So we have to build a foundation to start building our building. So your foundation is in this lecture. Please read it before you proceed with me to the next lecture. Thank you and see you next time.